Hi, this is Dr. De La Corte with Physics 313R, our introduction to quantum computing for everyone. So let's jump right into it. So about myself, I'm an associate professor in the Department of Physics and Astronomy at BYU, and my main research interest is in the design of enzymes. And while studying the limitations of computational approaches to designing enzymes, I realized that quantum computing holds some promise to allow us maybe in 5 to 10 years model complete reaction paths within enzymes. And so I think it's a great time to get invested in this field and to learn the basics. And while doing that, I came across this wonderful book by Chris Bernard called Quantum Computing for Everyone. And so our plan this semester is to explore this book, to revisit some of the chapters in it, and to explain them so that you can get two different channels of learning. One is reading the book, the other one is listening to a lecture on it, and then having in the classroom discussions about it. And this all should empower you to take a journal and write out what you learn while reading the book. And so the end of this course is going to be, will be, at the end of the course, you will have to have a deliverable, which is this study journal. And throughout the lecture, I'll give you some questions that you can answer. And then as you work through the book, I encourage you to repeat all of the calculations done in the book. Try to do them yourself after reading the chapter or after going to the lectures. And that will help you to really get some level of proficiency, especially with the linear algebra that may or may not be second nature to you yet. Okay, so let's jump right in. General guidelines. The book has good examples in it, but if you just read them and don't really try to do every step of each calculation, you will get lost as the book continues. So it's really important, especially in chapter 2, that you do all of the examples and that if the book says, hey, it would be a great idea to try this for the other two cases, that you do that by yourself so that you can get some practice with it. Okay. Also, when you come to in-class discussions, be ready to discuss with us, right? We want to use the in-class time to revisit these slides, but then also give you the opportunity to raise questions and concerns and take the time where it's most beneficial for you so that we all, at the end of this semester, understand the introduction to quantum mechanics and quantum computing very well. Great. So why quantum computing? What's so interesting about it? We will or you might have heard already about certain words that are somewhat of mysteries in your mind. They're not quite defined. When someone, for example, throws the word quantum teleportation at you, you might have Star Trek like images of someone beaming from planet A to planet B in your mind. Or when someone talks about the entire internet will be broken up because someone has bought or built this first quantum computer with quantum supremacy. What does it really mean? So hopefully by the end of this semester, you will be able to give very nice definitions of terms like qubits, quantum entanglement, quantum algorithms, and some specific algorithms like Shor's or Grover's. While we won't go into all of the nitty-gritty maths of those algorithms, we want to give you the tools so that you will be able to understand them by yourself if they become relevant at some point. But for sure, at the end of this class, you will be able to put these words into context and help other people understand what they mean. Great. So, fundamentals. The first thing we have to embrace is that quantum mechanics is completely counterintuitive. If it's intuitive to you, well, you're probably an interesting person. I would like to meet you. But to most people, it's very, very counterintuitive. And because of this counterintuition, the type of reasoning that you take, that you use in introductory to physics class when you get exposed to Newton's laws, just doesn't work well. So words and experiments are not sufficient to explain and predict what comes out of the results of the theory of quantum mechanics. So we need to have a different language to communicate it efficiently, and that is math. And so there is a subset of this field of linear algebra that we will have to actually master together. And while this is an introductory course for everyone, I understand that that won't be super simple. And so we're going to spend a whole week just on understanding this math foundation. And then the remainder of the course, we will reiterate until hopefully after 7 weeks, we will fully understand the part that is necessary for the core introductory concepts of quantum computing. All right. So in a nutshell, what is quantum computing? It is actually a fusion between the fields of quantum mechanics and computer science. So all of these crazy physical phenomena that have been proposed and put into very impressive action around 1940-ish, plus everything that has happened in the world of computer science, especially over the last 2 decades, is being merged together. And so a lot of these intersectional topics like quantum machine learning, quantum deep learning, all of these concepts are being published on all the time, because we sometimes hit limits with the computational hardware that is currently around. And the hardware that is built on the concepts of quantum mechanics can potentially overcome those. And so what we're going to see throughout this course is that while computer science and classical computing are super useful, they're actually just a subset of the more general form of computing, which is quantum computing. And we will see, for example, that the smallest units of computation, which is called the bit in classical computing, is just a special case of the quantum computing smallest unit, which is the qubit. But let's take a look at what this qubit is. Let's have a first encounter with it. It's a concept that will come back over and over. So the first thing you need to understand about a qubit is that it is not just like a light switch that can go on or off. The classical bit that's used in your normal computer, that is oftentimes represented as a switch, an on switch or off switch. The thing with the qubit is it can live in every state in between being on and off. And so we call this in-betweenness a superposition. A superposition, you might recall from introductory physics or linear algebra, is when you have two vectors and you add them together. If you have, for example, a direction that points there and a direction that points there, then a direction that points here could be considered as a linear combination of this direction and this direction. And that is a superposition of these two other directions, which we were going to encounter in greater detail later on. But in general, you can assume that this qubit is living on something that is kind of like a sphere that has poles that are equivalent to the classical 0 and 1, but then it has a defined radius that swings all around and can point to all of these other places. The interesting thing about qubits is that while they can be in a state of superposition, where they can point pretty much anywhere, as long as the radius is defined, anywhere on the sphere, in the moment where you measure them, they become either 0 or 1. And that's going to be one of these really counterintuitive things on which everything else in this course will be based. So we have to understand that. Okay, great. Another important thing about qubits is 2 bits, they are always separate. So if you have a switch here and a switch here, you turn this one around, then this one will be whatever it is. It can also, so you can turn this on and off, and you can turn this on and off, and that is totally independent of each other. With qubits, there can be this interesting phenomenon called entanglement, which again will come in greater detail later, but the initial concept is that this qubit, so maybe make it a sphere, and this one here, they are getting entangled. That doesn't mean that they're like stuck in each other. They're still separate entities, but there's something that combines them in a way that transcends distance. And so if you have these 2 qubits and you somehow entangle them and then separate them and put them far away from each other, if you get one of these to, for example, turn into the on position, that might make this guy also turn into the on position if they're entangled. Or if this one turns off, this one will turn off. And this ability to have one qubit change a state, and as it changes it, the other one also assumes the same state. That is the basic idea of quantum entanglement. And that is something that's completely out of the ordinary. You've never experienced that in normal life unless you had a really crazy electrician work in your house. Okay, light switches, they operate independent of each other, but qubits, they can operate together. Cool. So you already noticed maybe that there are a few words that have been used repeatedly, and they will be used repeatedly throughout this course. So I want you to pay particular attention to them and make sure that you define them really, really well in your journal. Superposition, so different directions being combined to give you a new direction. Entanglement, the behavior of two switches that returns qubits, and these qubits are interacting together. And then measurement, where measurement is the act of taking a qubit, which is somewhere on the sphere, and then doing a measurement that either knocks it into the on or the off position. So these three concepts will come over and over. All right. So one thing that is really beautiful about science is when you can make connections on a theory level that look surprising, and then afterwards you find a way to actually devise an experiment that measures these insights. And if then the evidence from the experiment sustains the theory, then you have seen something really truly beautiful happening. It's a type of revelation, right? Where you come up with an idea and then you test it, and then you have knowledge afterwards that it's ever right or wrong. And one of the really, really cool examples of that we're going to cover in this class is Bell's theorem, where you might be familiar with that saying of Albert Einstein that God doesn't play dice and there is no absolute randomness in the universe. That cannot be. While other people subscribe to this so-called Copenhagen interpretation of quantum mechanics, where they say, no, there is absolute randomness. Quantum mechanics is based on randomness. Niels Bohr was a big proponent of that. Well, these philosophies of determinism and randomnism, they were at odds with each other for a long time. And then eventually someone devised a theory, it was Bell, that said, well, these different theories or philosophies, they can actually be tested. And then he came up with an experiment, which later on actually showed a surprising result. I'm not going to give away what it was yet, but we will see later on how this discrepancy between the Einstein and the Copenhagen interpretation of quantum mechanics was effectively settled through this Bell's theorem. And we will see how a quantum computational circuit can help with that experiment. Then quantum teleportation. Getting you information from A to B or moving a qubit from A to B without actually traveling there, but somehow mysteriously using this entanglement to get information to cross the universe is really strange, really fascinating. So the math behind it will be quite beautiful. And if we learn a linear algebra, we will truly appreciate it. It's great. And some words, they just sound so amazing, like super dense coding. What is that? Well, we will also see that some words that sound like incredible, super dense coding. What does it mean? Can I put my neural network on like 5 megabytes of RAM or something? What is super dense coding? Well, we will learn that that might only be a way of saying you send 2 bits for the cost of one. But hey, we're going to know at least what it is at the end of this course. And yeah, then there's some really cool algorithms we're going to explore as well. Okay, cool. So what are the key takeaways from this course? Will you be proficient to work for IBM and build the next supercomputer, quantum-based supercomputer? No, you won't. But what you will be able to do at the end of this course is to appreciate the beauty of quantum computing. You will realize that quantum computing is the most fundamental way of looking at computing, in a sense, the father of classical computing. In that sense, you will appreciate that the qubit is truly the basic unit of computation and not the bit. And you will start to appreciate some of the software that can be built with quantum computing, some of the algorithms we're going to study. So here's the first assignment for your study journal. In your own words, please try to describe what the difference is between a bit and a qubit. And there are lots of people that come up with metaphors. Most of them work somewhat. See what type of metaphor you come up with. I'll be interested to read that. Cool. So that was lecture 1. I'll see you for lecture 2 later.